Okay, so now I'm just passing the rights to you. There you go. So now you only have to go back to that share screen button.
Is it okay now?
Yes, sir. Absolutely.
Okay. So I go back where
Thank
I stopped, right? Okay.
Yes.
Okay. So typically for these applications, the interior surface of these heavy wall vessels will have typically an austenitic stainless steel overlay. And that is the purpose. The purpose is to provide additional corrosion resistance for the intended service. Now, this, as an option or as an alternative to austenitic stainless steel overlay, roll bonded or explosion bonded clad plates also may be acceptable, but this is outside the scope of this document. And typically multi-layer vessels are outside the scope of this document also. But however, as you all of you know that generally these vessels for these equipments, the internal cladding is provided by stainless steel overlay, which is a continuous overlay process involving very specific welding processes like electroslag cladding or some other welding cladding as needed. Following grades of material are generally covered by these particular specification. As you can see here, 2 chrome 1 moly quarter vanadium, that is a grade 22, grade F22V. V stands for vanadium modified, and F22 is 2 chrome 1 moly grade. That is the most popular, although I would think that in the industry for certain, in some refining circuits, grade F3V, that is the 3 chrome 1 moly quarter vanadium, that steel is also used. But by and large, F22V is the most common material which the fabricators are familiar with, and this is used heavily for fabrication of hydroprocessing reactors involving this intended application. Base material for these grade of steel has to be absolutely precise and has to be absolutely, made to the, I would say, the best engineering practice. And typically, all these material which are used in this circuit or in this application, they go through a process called temper embrittlement when they're exposed to the temperature range of 450 degrees C or so, right? Or somewhere in that range. And basically, chrome moly steels are very prone to, very well known for temper embrittlement in that particular range. So temper embrittlement is a is a phenomena which is typically orchestrated by so-called low melting tramp elements. Basically, many of them are in the form of the impurities in the steel. And those impurities definitely cannot be removed entirely, but they could be controlled. So that is why all these steels have to be certified, or all these steels have to be manufactured conforming to a J factor. They call, basically that's a factor for temper, indicating the temper embrittlement. And typically the J factor for these steels has to be less than 100. And you can see the formula, which typically depicts or typically shows what is the J factor and what are the typical requirements. There could be some intentional addition of unspecified elements to enhance specific properties, but if it is done, that has to be recorded and have to have the purchaser or the end user's approval. And if approved, all these elements should be recorded on the material or the MTR or the material test report. Typically, these steels are all normalized and tempered. or they're basically subject to accelerated cooling from austenitizing temperature, then tempered, and basically commonly they're known, commonly they're called as quenched and tempered steels also. So basically we've got two categories of steel, that is normalized and tempered and quenched and tempered category. So out of which, to the best of my knowledge, the second category is most preferred for the intended equipments. And the tensile strength, in line with the heat treatment process adopted, the tensile strength definitely differs. And as you see here, for the conventional steel, the typical tensile is about 100 KSI, and for advanced steel, it is 110 KSI. The yield strength at the same time is kept in the range of 90 KSI or so. That is definitely a property which is needed and which has to be watched out as in the procurement stage for the steels. Impact properties, that's a very critical aspect of these steels. And basically what happens is that the requirement out here is that 40 foot-pounds or 55 joules, or with no that 40 foot-pounds or 55 joule is the average, and with no single value below 35 foot-pounds or 48 joules at minus 29 degrees centigrade. That's a CHARPI impact requirement. And at the same time, the percent of ductile fracture and the lateral expansion, that also has to be reported in the MTR. While these steels undergo fabrication, there is a critical test which is called step cooling test. Step cooling test is a test, or is a fundamental test, which detects basically the ability of the steel to withstand or resist the temper embrittlement. So temper embrittlement, as you can see here, the step cooling test basically is highlighted here, or is shown here. These are the various steps. If you go back at these, if you look at this figure, what you see is that this is the typical circuit, or this is typically the time and temperature showing the temper embrittlement, or step cooling test. So the step cooling method. So what you can see here is that basically the steel following the fabrication, immediately after fabrication, the steels or the vessels or the intended welds, they are post-weld heat treated at this specific temperature, then cool down to the ambient temperature, or typically the room temperature. After that, whatever ND and whatever requirements have to be fulfilled. Following that, they are taken at the step cooling temperature and exposed to this kind of heat treatment cycle. Of course, this is not done on the main equipment. This is done during the procedure qualification for procedure qualification for welding. And these particular steps, these are the steps as you see here. These are typically the step cooling test and a step cooling heat treatment. So that means you start from a temperature. You start from a temperature, raise it up to 593 degrees centigrade, then hold it there for certain specific hours, about 6 hours. Then again at 593 degrees centigrade, you hold it for an hour. Then 583 degrees centigrade, it's about 15 hours, 523, 24 hours, 495 is 60 hours, and 468, which is close to the temper embrittlement zone or temper embrittlement temperature range. You have the maximum exposure of 100 hours. And following that, you do a set of CHARPI impact tests. Typically 8 selected test temperatures. You do a CHARPI impact test to kind of establish the impact test temperature curves. That means what happens is that when you start with a higher temperature, you will have a higher absorbed energy. As the temperature falls, typically just your impact values go down, and that's the way you develop the curve without step cooling. But of course, with the post-weld heat treatment, following the step cooling, you have to do another set of impact tests to establish the transition curve. So this first curve is called VTR 54, and this is also VTR 54. That is 54 basically indicates the CHARP impact impact test or CHARP impact values 55 joules at this particular temperature. And the typical requirement is that the difference between these two should not be greater than 10 degrees plus 10 degrees centigrade. And here, what is the definition? That basically that 55 joule temperature is the CVTR40. And another is that, del CVTR40 is your 55 joules or 54 joules called, CHARP impact temperature after the step cooling or temper embitterment test. And the difference between these two should not be more than 10 degrees centigrade. That's a typical requirement. And what is done is that after setting all these, after going through all these impact requirements and establishing these particular curves, these shift, as you see, that should not be more than 10 degrees centigrade. That's a very specific requirement, And as you can see here, these are different. This is taken out from a literature by Kobelko. And you can see here that how the shift in curve is happening. That means you can see that basically in the form of as you do the step cooling test, there is a gradual shift in the impact values or the impact properties. That means basically it is going down compared to the impact test without any step cooling. Having said all those, these are typical requirements for and very specific requirement. In order to fulfill all these, we need to have many things under control. The most important thing is the welding consumable. And basically the welding consumables, they typically have a factor called X bar. And that is very well-known factor to all the fabricators and the welding consumable manufacturers. And the X bar out here should not be less than, should not be more than 15 ppm. And rather, this value, empirical value, should not be more than 15. Whereas you see here, all the tramp elements, the values are in ppm, and a total summation divided by 100 should not be more than 15. That's a typical requirement. And also at the same time, your low hydrogen consumables have to be used. Absolutely, it is a well-known fact. And the diffusible hydrogen should not be, more than 8 ml in 100 grams of weld deposit. And typically, as you know, that all the welding consumables used for this intended application, they are either H4 or H8 grades. This is a typically a typical figure or typical outlay of a reactor. As you can see, many of these are these days get fabricated in India. So there are many fabricators, many welding engineers, and many metallurgists also who are very well versed with these equipments and the manufacturing and fabrication practices. So I'm not going to go into the details of it. But this is, as you can see here, that's a massive reactor, and definitely the weight could be easily more than 1,000 tons or close to that, or even maybe more than that also, depending on what the shell thickness involved and what is the size involved. These welding heat treatment and production testing requirements for these reactors are massive, and basically they're very stringent. So I have tried to capture some of these requirements from this recommended practice. And as you can see here, that MPI, I mean, 4 basic methods, MT, PT, UT, and RT, they are very commonly used. And as you can see here is that welding procedure qualification typically involves qualification to ASME Section 9 and as well as ASME Section 8 Division 2, paragraph 3.4 or ASME Code Case 2551-1. These are very specific code cases which tells you exactly what what are going to be the requirements, and basically, you know, one can find out all these details. Where, I mean, if you just search in the net or if you search in the ASME respective website. And as a matter of fact, during the procedure qualification, the basic requirements is that the base metal should have the same ASME material specification, same P number, group number, and nominal composition, as specified for the vessel. Except that this could be either plate or forging. I mean, you can use I mean, either shape for qualification of weld procedures. Welding consumables for each welding combination, where flux and whichever are used, shall be the same type of brand as those which is used in the production welding. That means what it indicates is that you just stick to one brand or one specific lot, one specific heat number, and as it goes, or one specific wear and flux combination for these reactors. That way, they're very, very specific and they're very stringent about this. A.R.P. impact test, definitely it is a mandatory requirement. Step cooling test, it is a requirement for each weld procedure and process specified, and every weld has to pass. And as I explained in the previous slides, that this difference or a shift in the impact values after step cooling test should not be more than 10 degrees C. And we can see here that typically heat treatment requirements for the advanced steels, we have for the PQ qualification, we have the minimum and maximum post-weld heat treatment. Both has to be, I mean, the steel has to undergo, or the coupon plate has to undergo typically minimum and maximum. So minimum is typically what is intended for the vessel, and you know, as per ASME Section 8, that is going to be adopted in the practice, or I mean, following the fabrication. And maximum is something like an empirical, you know, estimation. That means basically assume that you have to do a couple of repairs or so, and in that way, how much is the maximum allowed? See, this maximum temperature definitely should correspond to the simulation coupon which is done in the mill for the test plates, as well as for the welding consumables which is done by the, you know, consumable manufacturer. So this minimum and maximum post-weld heat treatment temperature is very specific, and added to that, basically we have the step cooling test also. So going back to this topic, in the welding procedure qualification stage, definitely hardness method, hardness as requirements, or I mean, hardness check and the cross section of the weld has to be done, and this is a typical layout of the hardness check. And as you can see here, you have to do number of readings, you have to do multiple readings, and basically what it says is that, and typically these are the requirements, that is 235 HV 10 with it for conventional steel, and 248 HV10 for the advanced steels. So advanced steels mean basically 2 quarter chrome, 1 moly, quarter vanadium, that is falling under that category. And that's basically the requirement for hardness. And this has to be met as well as during the procedure qualification and as well as on the production welds. Now, During the fabrication, what are the methods or what are the steps to be taken? The preheat and heat treatment basically is very, very exquisite or very specific for this. So minimum preheat temperature should have something like 177 degrees or 150 degrees C, that is 150 for the conventional grade and 177 or 350 F for the advanced grades. And during welding, the preheat temperature has to be maintained continuously, thoroughly, during the process of fabrication until post-weld heat treatment international, ISR, that is intermediate stress relief, or dehydrogen heat treatment, that is a DHT, is performed. Now, basically all these methods definitely minimize the reduce the risk to hydrogen cracking and minimize problems due to low toughness values. And typically all this preheating, all these so-called the preheating band has to be maintained up to 4-inch wide band in any direction of the welding. That means basically when you weld a seam, 4-inch from each side of the weld, at least minimum, as a minimum, need to have these temperature, need to have this particular temperature need to be maintained in that zone. And intermediate stress relief, or ISR, is required before cooling below the preheat temperature. That means and prior to post-weld heat treatment. And what happens is that following the post-weld heat treatment, the steels undergo an immediate, following fabrication, the steels undergo, or the welds undergo an immediate ISR. And ISR, what the requirement is that shall not be weighed for strain joints such as nozzles, etc., and all those things. So what it implies is that ISR is something like a soak, long time soak, and basically for conventional steel, this ISR involved is 593 degrees centigrade or 1100 degree Fahrenheit. And for the advanced steel is 650 degrees centigrade for a minimum of 4 hours, or 680 for a period of 2 hours. And this ISR has to be done, and this has to be performed immediately after welding, before subsequent post-weld heat treatment is done for for the shells or for the components which are fabricated. Now, sometimes the people may think, okay, instead of the ISR, why not I do the DHT, dehydrogenation heat treatment? And DHT, that involves a temperature or heating, continuous heating to a temperature of 300 degrees centigrade and or to 350 degrees centigrade, and it is 1 hour minimum, or 4 hours, 1 to 4 hours minimum. But whether it is DHT or whether it is ISR, it is again as manufacturers, it is again the end user or the purchaser's call, and which the fabricators definitely has to, they have to fulfill the requirement. But from my experience, what I have seen between DHT and ISR is intermediate stress relief is the preferred and conventional, is the preferred method for these reactors. So the production testing on the base metals, whatever is needed are highlighted here. You need to have a chemical composition of the weld deposit for each welding process adopted. And in the weld deposit, chrome, moly, vanadium, niobium content of these weld metals, basically they should meet ASME section 2 part C. That is the applicable ASME, applicable ASME code for welding consumables. That means basically, if it is SFA 5.5, is the requirement for the SFA 5.5 to be followed for welding consumables. The welded joints definitely meet the alloy content, the chrome, moly, vanadium, and niobium content to that requirement. After final post-weld heat treatment, hardness testing is a must, and each hardness test will have an average of 3 impressions. And as I said before, that is the hardness shall not exceed 225 Brinell or 235 Brinell for the advanced as well as the conventional steels. Well metal production impact test, that is again a must. And during this impact test, the production, one need to find out the values, and basically step cooling test, as I mentioned here, only well metals are required to be tested as far as the production coupons are concerned, or production coupons are to be tested. Weld overlay is a critical part of it, as everybody knows that austenitic stainless steel SS347 is overlaid on these reactors. And that is predominantly to mitigate the hydrogen damage. And typically they need to have a control of the ferrite number, and the ferrite number typically for SS347 should not, the minimum ferrite number should be 5 FN, because below that 347 typically has a tendency to develop hot cracking. And as this RP tells that, this 5 FN may be reduced to 3 FN. 3 FN is a relatively lower ferrite number, but the vendor has to prove that there are no tendencies of hot cracking, and as well as it requires the purchaser's approval. But by and large, the industry, the requirement is the 347 well deposit, the typical 5 FN ferrite number. Disbonding test, when required by the purchaser, hydrogen disbonding test is needed for the overlay weld procedure. And that's a very specific test, which is, details are mentioned in ASTM G148. And it's a very specific requirement. And I'm not going into the details of that. But as a matter of fact, disbonding test is a quite important test for the weld overlay, and they have to pass that. And typically, as I mentioned before, that welding consumable procedure qualification, preheat heat treatment during weld overlay, chemical composition of the weld overlay, then ferrite content of the weld overlay. These are the specific requirements, and these are the typical requirements which has to be fulfilled during the procedure qualification as well as production welding of these welds, on these equipments, I would say. And post-weld heat treatment, as I mentioned earlier, is for the conventional steel, it is 690 plus or minus 14 degrees centigrade. So I'll say the 690 to 690 to 705 degrees centigrade. And for the advanced steel, it is a little higher, 705 to 720 degrees centigrade. And typically, the requirement is 8 hours of minimum soak for, and the maximum could be anything depending on, depending on the client specific requirement or the project specific requirement. And this is a quick summary of what are the testing required. And as you can see here, this table is taken out from the same RP 934A. And you see here, weld procedure, you start with the base material. You see the plate, forging, piping, right? You have everything, tensile, impact, PMI, then chemical composition, RT, UT, as well as, any test you talk about, they are needed for the raw materials for the plate materials as well as forging, as well as piping and other components. When you talk about the welding consumable, you require tensile, impact, PMI, chemical composition, and as well as you need the step cooling test also. Weld qualification test plates, you need the tensile, and you need hardness and others. Basically, you have to have, the step cooling requirements. And weld overlay, you require chemical composition, ferrite, and other ND tests as mandated by the project specification. And production welds, you see here, ages, weld edge preparation, you need MT or PT. And for the back gouge surface, you definitely need MT. Before post-weld heat treatment, you need chemical, you need PMI, you need the chemical, you need UT, you need MT, you need PT, as well as after post-weld heat treatment, all these three steps, that is UT, MT, PT, and hardness. These tests have to be performed. And this is a requirement for the production weld overlay. And before weld overlay, you have to do MPI or or PT. Generally, PT is preferred. I would that's from my experience I have seen. Before post-weld heat treatment, you have another set of requirements, that is, you need to do PMI, chemical, ferrite test, and UT. And after post-weld heat treatment, you have to do ultrasonic. You note here the production weld, the ferrite test is to be done before post-weld heat treatment. Generally, after post-weld heat treatment, there is a tendency to for some increase in the ferrite due to certain specific reasons. But that is why the recommended practice is to check the ferrite before post-weld heat treatment. And other you see production test plates, you need the base metal welds, you need the impact test. So in a nutshell, I would say that the requirements of the NDE on other tests, the destructive as well as non-destructive tests, are very extensive for this fabrication of these reactors. Hydro test at the same time is a very important aspect of it. And as you know, basically test water have to have a chloride limitation, should not be more than 50 ppm, should not contain more than 50 ppm of chloride. And typically the hydro test, during the hydro test, the vessel metal temperature, that should be 15 degrees centigrade or warmer. So that in no way they should go below 15 degrees centigrade, or else in such a thick reactor, you can have a tendency for a ductile to brittle, transition. Because as you know, hydro test exerts immense pressure, and if the temperature of the media is low, that can trigger any kind of a failure in the material. So that is why hydro test temperature has to be, water during the hydro test temperature has to be closely monitored, and it should be in this particular range. And the vessels should be thoroughly drained and thoroughly dried immediately after testing. And preparation for the shipping, following the hydro test and following thorough drying of the vessel has to be nitrogen filled, and it has to be and this has to be all the so-called the machine surfaces, they have to be protected by the suitable grease or the rust preventive oil or coating as mandated by the specifications, project specification. And that's the way they get ready for shipping. And last of all, these are the typical documentation requirement one has to submit to the client. And you can see that basically what is you can tell very well that everything is included. That means basically the material test report should indicate chemical composition, mechanical test results. You need the J factors, that is the temper embrittlement factor for the test plates or for the base metals. You require the X bar or the temper embrittlement factor or temper embrittlement values for the welding consumables. You need the impact test results before and after step cooling. You need the hot tensile required test if it is mandated by the client. That is, typically it has to be done at the service temperature or the temperature which the end user or the client feels is required for this test. We require welding procedure specification, all the reports related to welding procedure qualification that has to be submitted. The PMI, positive material test reports for the welds, base metals at various stages of production. You need the hardness test results. You need the ND reports. You need the heat treatment data, which includes the post-weld heat treatment, ISR, intermediate stress relief, and the DHT, dehydrogenation heat treatment, if adopted. And last of all, the production test results also. So in a nutshell, I would say that this vessel, fabrication of these vessels require very specific skill, absolute maturity on the part of the fabricators or the vendors involved. And it's a total, I would say, thorough knowledge of materials, as well as welding practices, as well as the ND methods. And in a nutshell, I would say that this is fabricating reactors, meeting these, conforming to these API RPs, as well as ASME Section 8 Deep 2, is the ultimate test for any fabrication companies, as well as any engineering companies involved. So with this statement, I've kind of reached the end of this presentation. I hope I know I had to run through pretty fast because there are a lot of other contents involved. I hope you have enjoyed it, and we'll come back to you. You may come back to me with any set of questions if you need at any point of time later. Thank you very much. Thanks for your attention. So I'll now switch over to move over to the other presentation as a part of this, today's presentation session. Thank you. All right, so I'm going back to another presentation from my side, and this time it is going to be
Any problem in sharing?
are you able to see now?
No, not yet.
Not yet? Just a minute, please.
Click share and then select. Yeah, it's coming now. Yeah, it's visible. Yeah.
Okay. Everybody is able to see now?
Yeah.
Okay. The next one is on API 934C. API 934C is typically the recommended practice for materials and which involves material and fabrication of 1¼ chrome, half moly, heavy wall pressure vessels for high pressure hydrogen service. And typically these vessels operate at a temperature below 440 degrees centigrade or 441 degrees centigrade or 825 degrees Fahrenheit. Typically these are needed for, these recommendations are followed for fabrication of hydroprocessing equipment. Typically what I know to the best of my knowledge are the hydro treaters, right, which are not which are one step below in terms of the technical requirements, or in terms of the integrity, in terms of the technical requirement as far as hydroprocessing is concerned, and they're one step below the hydrocrackers. Typically, these vessels operate at a relatively lower temperature, and it involves slightly leaner material, 1¼ chrome, half moly. And what he says is that basically these recommended practice presents material and fabrication requirement for new 1¼ chrome half moly steels for heavy pressure vessels and heat exchangers for high temperature, high pressure hydrogen service. These vessels could be designed fabricated to either ASME Section 8 DIB 1 or DIB 2. That is again a designer's choice and a designer's call. And at the same time, end user's call also. This document may be used as a resource for fabrication of 1¼ chrome steel also. Interior surface of these vessels may have an austenitic or ferritic stainless steel overlay or cladding to provide additional corrosion resistance. But in most of the cases, it is not may. They generally have an austenitic stainless steel lining or austenitic stainless steel overlay. And the scope, this is refined, this is restricted to shell thickness of 2 inch and above, and but less, between also 2 inch and above. So it's typically 50 millimeter or 2 inch as a minimum, and 4 inch or so as a maximum. And at the same time, also the nozzles, flanges, etc., all other ancillary, all other products needed for fabrication of these exchangers or the vessels, they are restricted to a thickness below 100 millimeter or 4 inch. Generally, why this is so, typically for thickness of 4 inch and above, historically it has been shown that 1¼ chrome and half moly steel they have a difficulty in meeting the toughness requirements. And this recommended practice or this RP is not intended for use of equipments which are above 441 degrees centigrade or 825 degrees Fahrenheit or in the creep range. There is another RP which I'll talk about later that is generally mandated or generally followed for fabrication of such equipments which would be operating at above 440 degrees centigrade. And as far as the base material is concerned, typically these are 1¼ chrome half moly. These are 387 grade 11 or in grade 11 class 1 or class 2. So class 1, class 2 is very well known to everybody. And forgings are generally class 2 and the matching composition F11 and pipes are also matching composition P11 type. The steel making practice is very specific. You need to have a very clean steel, and at the same time, the steel has to be vacuum degassed. That means basically to control all the tramp elements, number one, and then number two, all to control the gaseous impurities in the steel, which can give rise to problem during fabrication or even during service also. As like the requirement specified in 934A earlier, you see here that the chemical composition is typically, for all the fine is below 15 ppm. That is the and here basically what you have is that this X bar requirement is applicable for the materials as well as for the welding consumables also. Now, heat treatment, generally all products, these steels are either normalized and tempered or quenched and tempered. And when the quenched and tempered steels are used, they typically QNT requirement is very specific. And generally speaking, when somebody is handling QNT steels, right, one has to be very specific or one has to be very careful in fulfilling the requirements at every stages of fabrication. CHARP impact test should be performed for these steels, and CHARP impact should comply with the applicable code and following the additional requirements as mandated by the project. And CHARP impact test for forging shall be typically transverse in the direction of the metal flow, and that is very you know it very well, because when you do the forging, there is always a grain elongation or grain orientation on a specific depending on which side on which direction the deformation is done. So typically the requirement is that when you do the test coupon of the forgings, you do you take out the specimen in the transverse orientation, so that at least you know for sure that the properties are, the minimum properties are being met, and they're being met well. And the minimum A.R.P. impact test temperatures at minus 18 degrees centigrade should be 54 joules, or average of 3 specimens, or 20 foot-pounds, or 27 joules for a single specimen. That's the minimum requirement. And in addition, if the minimum design metal temperature is below minus 18 degrees centigrade, code requirements for impact testing is a must for for the design code, and as mandated by your project specification. If the impact testing at this temperature meets that this particular requirement, this particular values 54/27 joules, that is the average and the minimum, retesting at minus 18 degrees centigrade is not needed. Well, this is a very specific requirement, that need to be looked at when it arises. And percentage shear fracture should be at 25%. Lateral expansion also should be reported in the material test report. And welding consumable requirement, basically the X bar should be 15, less than 15, where it is typically, you see here, X bar is a summation of these phosphorus, antimony, then tin and arsenic, all these tramp elements, and are divided by 100, and this should be this particular number should be below 15. And additionally, carbon should be restricted to 0.15% maximum. Copper is 0.2 at maximum, and nickel basically should be 0.3 weight% as maximum. And generally, the restriction of copper is to control the hot cracking tendency at the elevated temperature. These equipments are exposed to a temperature of 400 degrees C plus, right? Restrictions of those are very important. And low hydrogen welding consumable, typically 8 ml or H8 type is the bare requirement, but H4 is most common, which most of the manufacturers are able to give for SMAW, and GTAW has got even lower than that, or it's absolutely nil if you go that way. FCAW welding consumables, H4, meeting the H4 grade is often difficult, so H8 is the bare minimum, and same applies for the submerged dark welding consumable also. And general welding requirements, basically all welds, for including non-pressure attachment, should be full penetration type. There should not be any consideration of partial penetration joint design in these equipments at all. And they should be welded in such a fashion, or the location would be such that full ultrasonic of the UT of the exam, ultrasonic testing after welds can be made after fabrication, after the installation is complete. And definitely they should be sufficiently smooth, ground smooth, to facilitate this kind of NDE, that is MPI, PT, UT, and UT or RT. Now, all welds should be completed prior to final post-weld heat treatment, except that welding of internal attachments to the corrosion resistance overlay or cladding may be done, subject to the discretion of the engineering. Subject to the discretion of the client as well as the other engineers involved. And for these attachments, a mock-up test should be performed that if, say for an example, these internal attachments are done after final post-weld heat treatment, this RP calls for a mock-up test to be done to show that it does not, these welding of this internal on the overlay does not produce any hydrogen, any HZ in the base metal. So that means basically you have to restrict, you have to control any welding heat input if you do the welding of this internal following the post-weld heat treatment. And all weld repairs shall be done using a repair welding procedure and qualified in accordance with this RP, and it should meet the same requirement as the normal fabrication welds. That means any welding repair you do, that has to be qualified prior to application on these equipments. And welding procedure qualification, as I mentioned earlier, if for 934 in course of 934A, and it says it should be qualified as per ASME section section 9, with the following additional requirements. The base metal for weld procedure qualification, that should have the same ASME base material specification, same P number, group number, and similar in the chemistry as specified for the vessel. That way, it is slightly lenient as compared to 934A. You may use either forging or plates as test coupons, and welding electrodes where flux combinations should be the same type and the same brand as used for the production welding. And transverse weld test should involve a maximum post-weld heat treatment condition and should meet the ambient temperature properties, that is impact temperatures also. A.R.P. V-notch impact test should be performed on the weld metal and heat effector zone in the maximum and in the minimum and maximum post-weld heat treatment conditions. These impact tests should be performed after each weld procedure and should meet the impact test temperature and acceptance requirements as per this particular clause 5.5.3. Yeah, that is, that's a very specific requirement. This particular clause talks about what are the impact values needed when you carry out an impact test. And hardness test is mandatory, and this hardness values or hardness readings should not exceed 235 Vickers. Preheat all base materials shall be preheated to a minimum temperature of 150 degrees centigrade. And this preheat should be quite wide zone. Basically, it should be something like 100 millimeter on any direction of the weld. Excuse me, just a minute. The preheat temperature shall be maintained until post-weld heat treatment or DHT is performed. And as you see here, the DHT or dehydrogenation heat treatment is mandatory for these vessels also. And if it is done, it has to be done at a 300 degrees centigrade for 1 hour as a minimum requirement. ISR intermediate stress relief is not required for these vessels, but instead of the ISR, the fabricator has the privilege to resort to DHT. But however, if the vendor if the end user or the purchaser decide to impose an ISR, then the requirement should be it is 593 degrees centigrade for 2 hours as minimum. The purpose of the DHT, as all of you know, is to drive out the hydrogen from the weld to minimize the risk of hydrogen cracking and to minimize the problem related to weld toughness. In line with that, we have the production testing requirements of the base metal welds. We have the chemical composition of the production welds, and chemical composition should be done by either laboratory test by chemical analysis or doing a portable analyzer, that is typically what we call as PMI. And the PMI definitely need to have a suitable accuracy and the precision needed. And the chrome and moly content in the welds shall meet Section 2 Part C requirements for the specific type of welding consumable used. Now, following final post-weld heat treatment, hardness measurement shall be done on the pressure retaining welds, including the nozzle and attachment welds. Each hardness test result should have average of 3 minimum 3 impressions on each test location. And those locations would include weld metal and base metal adjacent to the fusion line on both sides of the weld. And all individual hardness values shall be recorded, and hardness values should not exceed typically 225 HPW. And these tests shall be performed on the site exposed to the process environment when accessible. That means basically we need to have the hardness testing predominantly done on the internal of the vessel, internal as well as on the external surfaces also. And continuing on that note, we need to have the impact test, production test, test plates, production coupon plates. They should be subjected to a maximum and a minimum and a maximum post-weld heat treatment. And they should be tested basically to meet this particular clause. And this particular clause is again on the impact values, that is 40 foot-pounds or 54 joules. And that particular requirement has to be met. Weld overlay or integral clad, they definitely are made of austenitic stainless steel. And austenitic stainless steel typically are used to deliver added corrosion resistance of the weld overlay. And as a matter of fact, for the austenitic stainless steel overlay, the ferrite content should be between 3 to 10 Fn. And depending on the grade, depending on the overlay material selected, these value can fluctuate, or these value can vary. So, but 3 to 10 Fn is a nominal requirement. And disbonding test is like 931A, like 934A. Disbonding test is not a requirement because experience indicated the risk of disbonding for these vessels at this thickness and the hydrogen charging levels are low. But if client wants the disbonding test to be done, then API 934A can be used as a resource document. Weld overlay procedure qualification, the selected weld overlay process and the number of layers should be qualified as per ASME section 9. Now, procedure qualification test must be made or should be made on the base metal of the same ASME specification as specified for the vessel, which could be either plate or forging. So if it is 387 grade 11, class 1 or class 2, it has to conform to the same specification, and that product form could be either plate or forging. And thickness of the test specimen should be typically 50 mm or 1/2 thickness of the base metal, whichever is less. So typically if it is 4 inch, that is that comes to 100 millimeter, or it could be 2 inch or 50 millimeters. So you need to take lesser of this thickness, particularly for the qualification of the coupon for weld overlay. And I would say that typically 2 inch or 50 millimeter is around, typically that's a ballpark figure, which is generally recommended or generally adopted. And what do you need to do, or what we do during the weld overlay procedure qualification? The weld electrode wear flux used for weld overlay procedure qualification, that should be the same type and brand to be used in the production. And so basically same type, brand, and preferably if you can use the same batch also, if one wants to be too restrictive. Qualification test shall be subjected to a maximum post-weld heat treatment condition. The chemical composition shall be checked, and it shall be checked at the minimum thickness, that is typically the qualifying thickness, what is specified, what is the requirement as per section 9, as well as the project specification. And these qualification thickness, the composition taken at this qualification or the minimum thickness, that shall meet the filler metal specification for the final layer also. So that means basically what happens typically, if you meet the qualification, composition of the weld overlay at the qualifying thickness. And as you go at the final layer should not be a problem. And the ferrite content typically should be between 3 to 10 ferrite number. And going back to the continuing on the manufacturing process, what you can see is that during the weld overlay, the base metal shall be preheated to 94 degrees centigrade for the first layer of the weld overlay. That is very important. You do not need, as a matter of fact, any preheat for the subsequent layers, but one has to control the maximum interburst temperature generally to, control any kind of a sensitization issue. And in order to achieve that, the maximum interburst temperature generally should be controlled below 175 degrees C. And as I mentioned earlier, no preheating is required for the second and any subsequent layers of weld overlay. Now, the earlier slide was on the weld overlay procedure qualification test. For the production welds also, one need to have the testing of the weld overlay, and it should involve chemical composition check, and chemical composition definitely has to meet all the specified or required chemical alloying elements like carbon, chromium, nickel, molybdenum, and niobium. And this has to be taken at number of locations, and basically one need to take at each shell ring and head one location of every shell and every head, and one for each manual welding process for nozzles. That is, what it means is that every weld what you do on this equipment, for this you need to do a chemical composition check at the end of at some stage of fabrication, preferably just at the end of the final fabrication. And ferrite content, as I mentioned, typically should be between 3 to 10 ferrite number of 3 to 10 FN. Next comes for the final post-weld heat treatment. The final post-weld heat treatment of these vessels typically are contained or typically maintained between 660 to 690 degrees centigrade, that is 1225 to 1275 degree F. And this is a very specific range for these particular equipments. And question may come that what else if I exceed that temperature? Generally, you should not exceed that temperature, because that if we do the post-weld heat treatment at a temperature below this, we may have issues with the notch toughness, or or the impact of meeting the impact test requirements for this for the welds. And I mean, for the parent material, it may not be that much of a problem, but for the welds, definitely is going to be a problem. And the fabricated vessel, you need to do post-weld heat treatment as a whole in an enclosed furnace wherever possible. Now, sometime it may happen the furnace is not long or big enough to allow post-weld heat treatment in a single, of the entire vessel. But in that case, sectional post-weld heat treatment is allowed or may be performed according as per ASME Section 8, Section 8 DIP1 or DIP2, that is the fabrication code which is adopted for design and construction. And during any post-weld heat treatment, continuous time temperature recording and monitoring definitely is a requirement, and that has to be monitored and that has to be documented. And ND or non-destructive examination, ND prior to fabrication, it should be UT for the base metal and the clad base plates. NPI for the entire surface of the forging, including the weld edge and other attachments, and mandated by this RP and the design codes. That is Section 8 DIP1 or DIP2. ND after fabrication and prior to final post-weld heat treatment, the final pressure retaining welds for the butt welds and skirt welds, that should be fully examined by RT. UT may be applicable in lieu of RT, where UT procedure fulfills the requirement of ASME Section 8 DIP2 paragraph, this particular paragraph. So UT and RT, they're kind of a complementary ND method. And depending on the resources you have the flexibility of using both, provided you meet the project as well as the design, the requirement of the design code. When RT is not practical for the nozzle skirt attachments, UT definitely can be a replacement or can be an optional method in lieu of radiography or RT. ND, after final post-weld heat treatment, base metal welds, you need to do, after final post-weld heat treatment, you need to do a full examination by UT as well as by MT also. Weld overlay, the entire surface shall be checked by PT. Entire surface of the weld overlay, that means basically welds on the overlay and the attachments to the overlay, they should be examined by penetrant test. Positive material identification, that is a must. So that should be done in accordance with the purchaser specification or PMI specification. And when you do the PMI, definitely you have to meet the nominal chemistry, as I mentioned earlier, that is these 5 elements: carbon, chrome, nickel, moly, and niobium, and other elements which the equipment is able to pick up in course of the examination. And hydrostatic testing or hydro test, basically the basic requirement, these are general requirements that you need to clean the vessels, and basically joints should be free from scale or any foreign matters before testing. All dirt, scale, sand, definitely they need to be removed. So that means the vessel has to be reasonably clean. And test water, the water used for hydro test typically should not exceed 50 ppm of chlorides. And during the hydro test, as like for 931A, the vessel metal test temperature shall be at least 30 degrees centigrade, or 30 degrees Fahrenheit, or 70 degrees centigrade. Just a minute, please. Shall be at least 30 degrees Fahrenheit or 17 degrees centigrade above the MDMT, or 15 degrees centigrade or 60 degree F, whichever is warmer. So that is a very specific requirement, and generally speaking, I would say that this particular requirement, 15 degrees centigrade, that makes the thing or keeps the thing very clean and straight. And the vessel shall be drained and thoroughly dried immediately after testing. And as you see here, preparation for the shipping. In order to do the shipping, the vessels have to be nitrogen filled, and these are the specific requirements for nitrogen shipping, for nitrogen filling. Last of all, these specific documentations are needed, like 934A. You see here all MTRs. You need the X bar results for the welds, for the base metals, and the chrome moly steels. You need to furnish the welding procedure specification with with all the procedure qualification records, and additional reports if needed by the purchaser, that has to become submitted also at the completion stage of the project. And those typically include heat treatment data showing the ramp up, hold time, and temperature, and that is required for the post-weld heat treatment as well as for the DHT. The PMI report, the production, the PMI report for all the welds, including the weld overlay as well as for the base metal also. And the production test results, that is the PTC, if it is required by the code. So in a nutshell, I ran through these, this recommended practice, that is 934C. I hope you have enjoyed this presentation, although it was a bit rush, I would say, because there are a lot of things to cover in course of this lecture. And I thank you for your kind attention. And with this, I have come to the end